How are we going to take this hardwired control unit and change it so that we can generate complex instructions and also more instructions without increasing the complexity of the actual control unit? So let's start off by having a look at the control unit. We're going to have our instructions coming in the bottom, and these instructions are decoded via this combinational logic. So the combinational logic here really is the heart of generating our instructions. If we head off to the left, we have all of our enables. So this allows us to enable information onto the bus from different parts of the CPU. So we can enable information from the registers onto the bus, or from the RAM onto the bus, or from the bus into the RAM, and so on and so forth. Now if we head to the right, then we have all of our sets, and this allows us to write information into each of the components of the CPU. So we can write information into the registers or write information into the RAM. And we have our little bit of sequential logic here, which is the counter, which controls that process. The first three are for us loading the information. So the first three is for our fetch cycle, and the last three is for our execute cycle. So where do we start trying to change this control unit? Well, we could take wires off and start introducing the idea of a microcoded control unit in a kind of random fashion, but I would quickly get lost, and I would imagine most people would get lost trying to unravel all of this wiring. So a simpler option for us is to get rid of all of the wiring and replace it with tunnels. So for example, I could take this wire off here, and I could name this wire, and I could name this wire here. So all of the wires in effect get names, and then we just stick the tunnels right next to the combinational logic elements. Now by doing that, we still have a functioning control unit, but we don't have all the wires cluttering everything up. And we can take all the different blocks and we can move them about as we so desire. And hopefully by doing this, it will give us some idea of how we're going to progress in order to generate a simpler control unit that we can extend a lot easier. Now, you're lucky because obviously I've gone ahead and done this. So let's go ahead and we'll have a look at the same control unit, but with all of the wires replaced by tunnels. So here we have the very same control unit that we looked at in the last caption, but I've replaced all of the wires with tunnels, and I've also moved sections round about. So remember, this is still fully functioning, everything's still connected as it was previously. It's just a bit easier for us to move things round about. So we have our control, the stepper sitting up at the top here. These are our inputs for our clock, enable and set. We have down the bottom here the 3x8 decoder, which we used to choose the instruction that we're actually working on. We've got our end test here. We have our instruction register coming in, the flag section, and a test for the flags, and a few sundry elements. Here is the output to our ALU, which chooses the ALU function. And we also have all of the outputs for the enables. So here's the enables here, and this is all of the outputs, and also for our enables for our registers R0 to R3, going through Reg A and Reg B. and we have our sets on the right hand side here, and these are generating our set commands again, which head out to the accumulator and the RAM and all of the registers. So it's still a fully functioning device, but you'll note here that I've started to take it apart in a particular manner. We've got here, if I make it just a little bit bigger, we've got here the values C0, C1. So these are what I've called just the instructions. So C0 is an ALU instruction, and the C1 is a load instruction. We got store data, jump, register, jump address, jump if, clear flags, and the IO instruction. Of course, actually the IO instruction is gone now because we're going to be using memory mapped IO. So that's a simplification. We will actually get rid of that. And also along here, we have along the columns, we have 4, 5 and 6. Now 4, 5 and 6 represent the positions in the stepper. So we have the rows, which are going to represent the instructions, and we have the columns, which will represent the stepper positions. So for example, if we went through a load command, then we would have at step 4, so there's a step 4 would go high, so that's the stepper, and we would have the value C1 would go high. So C1 is really the test for a load command. So in effect, it's the instruction coming in for a load command. So this is instruction here, and whenever that would go high, then we would have an output, and the output within the control unit, it would make Reg A would be enabled and the memory address register would be set. And then it would go on to the next option, which would be 5. And again, we would have C1, which tells us it's a load, and we would have 5, which tells us it's coming from the 5th element here of the stepper. And in that position there, we would have Reg A would be enabled, the C term here would be enabled, the flags would be enabled, would be set, and the accumulator would be set. And this other thing here, which we call C, would have this output. So I've just generated the same circuit, but using these tunnels. And point 6 would then go through this process. Point 4 and 5 would go through that process to generate the load. Now, if we look at this here, you might actually start seeing that there's something here that we've seen before. We've got a set of rows, and the rows choose the instruction, and we've got a set of columns, and the columns tell us which part of the instruction we're actually working on, part 4, 5 or 6. So let's have a look at this in the next screen, and it'll become more apparent what it is we're doing. So again, this is the same functioning control unit. We have our sets and our enables down here and some of the other items along the bottom. But what we're interested in here is this little section. So let me zoom in a bit so we can have a look and see what we've got here. So we're going to have along the top the stepper, and the stepper's got our first three for our fetch, and then the next 3 for our execute. So the 3 for our execute here I've actually got connected here, and those are the vertical lines. Now on those vertical lines we also have going across them the horizontal lines, which are our instructions. And if you see the point where they don't actually touch each other, but they cross over one another, we can stick our AND gates. And these AND gates are going to give us an output. So for example, we talked through before, the first one, the value C1 here was the load command. And in the load command, it's point 4, we had Reg A enable, memory address register set. And then the next point would be RAM enabled and Reg B set. So if you look at these, I think by now you probably come to the realization that this is nothing other than a little matrix. And I've called this the execute input matrix. So this is nothing other than, or it could be generated simply using a RAM block. Because all we have is the value C0, which would give us an address within the register. So it just gives us a line to go to. And then the value 4, 5, and 6 would be the next line of the instruction, and then the next line of the instruction. So in effect, the first one, for example, would be an ALU instruction. So C0 would give you the beginning of the ALU instruction. So C0, sorry, and 4 would give you the beginning of the ALU instruction, which would do this. And then the very next line in that memory would give you the next part of that ALU instruction. So the very next line would be determined again by C0 and the value 5. And the output in that line would be given by this here, which would be reg A enabled, C enabled, flag set, and accumulator set. And then the next line in the instruction would be given by C, the address of it would be given by C0 and the number 6. And we could jump about these instructions just by knowing the position of each of them. And we know the position by each of them because we know the value C0, 1, 2, 3, all the way up to the top instruction, and we've got the values 4, 5, and 6. So this is just a little ROM, a little RAM, and we can use this RAM within the control unit. So we can replace this thing here with a RAM, but we can keep the rest of the control unit here. So I'll go ahead, and I've already done this, so we'll go ahead in the next section and I'll show you us replacing this section here with a little, it's actually a little ROM block, so it's a read-only block, so we just put the information in and it just stays in there. So this circuit here should look a little bit more familiar because it's similar to the previous circuits that we've already built up. You can see here the stepper now runs through all the way up to 16. Now we're not using all the functionality of the stepper at the moment, but it does give us this option to increase the complexity of the instructions. And you can see along the left hand side we're still going to have all of our enables, and along the right hand side we're going to have all of our sets. But you can see here that a lot of the combinational logic here has disappeared because we've replaced that combinational logic with an internal ROM. So this internal ROM here is controlling all of the sets and the enables. And all we have to do in order to generate our instructions is we have to point to the correct address in this ROM. So when we point to that correct address, it will automatically put out the outputs we require. That is all the zeros and ones. All those zeros and ones will come out and they'll head up to all of the enables and all of the sets. So it means that each time we go into a position in the address of this ROM, we just change the enables and the sets, which are the outputs of the control unit. And all we have to do in order to build up our instruction set is to load up this ROM with all of the required zeros and ones, which will perform all of the functions of the instruction set. Now, again, that's an awful lot of words, and you're just kind of watching me doing this on the screen. So it's much better for us to go through an actual simulation because there's other little details here that we have to take care of. Now, I'm not going to do this in this video because this video has gone on for long enough. In the next video, we'll have a look at this design and we'll go through it in a bit more detail. But this is our micro-coded control unit. And it's not the final version of this micro-coded control unit. We're actually going to take some of the functionality away from the ROM here, and we'll just replace it again with some hard wiring. And this is the point I made in the last video. We want to come to a nice balance between the hard wiring and also the ROM. Because as it stands here at the moment, if we go to extend this design so that we've got maybe 8 or 10 or 12 registers, and we've got other sundry registers that we might want to use as well, then this ROM is going to get very complicated. And we can simplify the whole thing by taking some of that complication within the ROM and putting it back into hard wiring. So that's the direction we're going to go over the next couple of videos. And this is the end of this video. So thank you for listening. I'll get you on the next video. Goodbye.